So good morning all of you. So in this lecture we will be discussing encipherment using modern symmetric key ciphers. So basically these are the objectives which we are going to cover in this video lecture. So whenever we are discussing about symmetric key encipherment, this can be done using modern block ciphers, and there are various modes of operation that have been devised to encipher text of any size implying either DES or AES. So we know that DES encrypts and decrypts a block of 64 bits, and similarly AES encrypts and decrypts a block of 128 bits. But in the real life applications, the text to be enciphered is of variable sizes and normally much larger than 64 or 128 bits. So that is why we have different modes of operations that have been devised to encipher text implying either DES or AES. So these are the 5 different modes of operation: the electronic codebook mode, ECB mode, cipher block chaining, CBC, cipher feedback, CFB, output feedback, OFB, and counter mode, CTR. So let us see how these modes of operation can be used. So the first mode is electronic codebook mode, ECB mode. So this is the simplest mode of operation in which the text, that is the plain text, is divided into n blocks, and each block consists of n bits. So and if the plain text block is not a multiple of block size, and then the text is padded to make the last block of the same size as other blocks, and the encryption and decryption is done blockwise. So as shown in this slide, the ith block of plain text is encrypted with a key to generate the corresponding ciphertext block, that is CI, and the decryption is done in the reverse order, that is we will decrypt the ith ciphertext with the key K to get the original plain text PFI. So in this example it can be proved that the plain text block at the ls site is exactly recovered at block bob site. This is because the encryption and decryption are inverse of each other. And the reason why this mode is called electronic codebook, because in this mode one can pre-compile 2 to the power k codebooks, one for each key, in which each codebook has 2 to the power n entries in 2 columns. So each entry can list the plain text and the corresponding ciphertext blocks. However, if k and n are large, the codebook would be fairly too large to compile and maintain. Now there are certain security issues in the CBC mode. And the first issue is that the patterns at the block level are preserved. So for example, equal blocks in the plain text becomes equal blocks in the ciphertext. So if the adversary is able to find out that say block number 1, 5 and 10 and they are same, so it could easily get the plain text blocks 1, 5 and 10 again the same. So this is basically a leak in security. Second issue is that the block independency creates opportunities for Eve to exchange some ciphertext blocks without knowing the key. For example, if the adversary knows that block 8 can always contain some specific information, then the adversary can replace that block with some other blocks and in the previously intercepted message. So this examples describe such a situation where the adversary Eve is trying to replace the block that contains the information of the payment with another block with a different payment amount. The next topic is the error propagation in the case of CBC. So in this mechanism, a single bit error in transmission can create errors in several of the corresponding blocks. However, this error does not have any effect on the other blocks. Then there is a ciphertext scaling. So a technique called the ciphertext scaling is generally used in the ECB mode when without padding. So in this technique, the last 2 plain text blocks, that is the PN-1 and PN, they are encrypted differently out of order as shown below. and we assume that Pn-1 has n bits and Pn has m bits, where m is less than n. So in this manner the ciphertext sealing is performed to encrypt a message which is not a multiple of size of n bits. The second mode is the cipher block chaining mode, and the CBC mode. So in this mode, each plaintext block is exclusive ORed with the previous ciphertext block before being encrypted. So as you can see in this figure, the output of the encryption, and this output is XORed with the next plaintext block before the encryption is performed. However, for the first block there is no previous block, so in that case we will use a dummy block called the initialization vector, in short IV is used. So this initialization vector is agreed between the sender and the receiver in a pre-specified manner, and generally at the sender side exclusive ORing is done before encryption, and on the receiver side XOR operation is performed before the decryption. And here we have shown the relationship between the plaintext and the ciphertext block. The initial block, that is C0, is equal to the IV, and later on the subsequent ciphertext block is obtained by encryption between the plaintext block PI and XORing it with the previous ciphertext block CI-1. And we can easily prove that the plaintext block at the Alice site is recovered exactly at the Bob site by this formulation. And for the initialization vector part, it should be known to the sender and the receiver beforehand. So for that, the ECB mode could be utilized and to send the initialization vector between the sender and the receiver. In terms of error propagation, in CBC mode, a single bit error in the ciphertext block CJ during transmission may create error in most of the plaintext blocks in PJ during encryption. So again, ciphertext scaling is applied in for the ECB mode also. So here we have shown the formulation of ciphertext scaling. So here the head function is same as described in the ECB mode, and the padding insert basically zeros at the end. Then we have the ciphertext feedback mode. So in such situation we need to use DES and AES as the ciphers, but the plaintext block or the ciphertext blocks are smaller than the number of bits. So the main idea is that what we do not encrypt the plaintext or we do not decrypt the ciphertext, but we basically encrypt or decrypt the contents of a shift register denoted by S of size n. So this encryption is done by exclusive ORing an R bit plaintext block with the R bits of the shift register, while the decryption is done by exclusive ORing an R bit ciphertext block with the R bits of shift register. So here we have shown the entire formulation of how the shifting is performed and how the exclusive ORing is performed for the cipher feedback mode. So in CFP mode, the encipherment and the decipherment use the encryption function of the underlying block ciphers, and we have also shown the relationship between the plaintext and the ciphertext block. The next mode is output feedback mode. So this mode is similar to the previous mode, and that is the cipher feedback mode. So however, in this mode each bit in the ciphertext is independent of the previous bits. This avoids error propagation. So as you can see in this figure, the output of the encryption that is directly used to shift the bits of the registers, and thus error is not propagated. Next is the counter mode. So in this counter mode there is no feedback, and the pseudo randomness in the key stream is achieved using a counter. So using this counter we generate a random stream. For this, an n bit counter is initialized to a predetermined value, that is the initialization vector, and incremented based on a predefined rule such as mod 2 to the power n. And to provide even better randomness, an increment value can depend on the block number to be incremented. And finally, the plaintext and the ciphertext block have the same block size as the underlying DES or AES encryption algorithm. So as to summarize the comparison between different modes, so this is the overall comparisons. So in case of CFB and OFB mode, the number of bits to be encrypted or to be decrypted is less than equal to n. For the other modes, and the data unit size is n, that is equal to the input taken by the ES or the DES algorithm. Thank you.